Let's begin with the second session. It's really a pleasure for me to introduce Professor Aarti Singh, who received her PhD in electrical engineering from the University of Wisconsin-Madison in 2008, where she was working with Robert Nowak, and later was a postdoctoral research associate in the Applied and Computational Mathematics program at Princeton. She joined Carnegie Mellon in 2009, where she is now an associate professor in the Department of Machine Learning. Aarti has done several fundamental contributions in machine learning, high-dimensional statistics, and in particular over the last couple of years in optimization problems in deep learning. She has received numerous awards, including the NSF Career Award, and she is here to tell us about local signal adaptivity and learning features beyond kernels. Aarti, thank you so much for joining us.
Yeah, thank you for the invitation, and thanks to everybody for showing up. I know it's around lunchtime in some places, but yeah, I appreciate you being here. So I'll talk about, as right was said, like about local signal adaptivity, which is an idea that came up from trying to mimic something in natural images and then try to argue why feature learning, which is the basic contribution of neural networks, right, makes them superior over kernels for this type of model class that's inspired by natural images. So I'll make it a little bit more clear as we go. So maybe let me start by just saying, right, the high level of first pitch here is that, we want to be able to show a separation between neural networks, which are adaptive feature learners, over fixed feature mappings, which is what kernel methods do. And of course, in the past few years, there has been a lot of interest in showing parallels between the two methods. So where the neural tangent kernel in particular, even our prior work, looked at that, talking about how using gradient descent for training neural networks under a specific, conditions of like wide enough network size and so on reduces the neural network to behave like a kernel, which is determined by the architecture and how you initialize your weights, right? But this is the sort of the kernel view, right? That we can view neural networks as kernels under these conditions. But of course, then it essentially boils down to that we are using fixed features, right? There's no feature learning that's happening, which seems to be the main power of neural networks. So what we wanted to, of course, go after is then that can we come up with a setting where feature learning, right, which is really the key to neural networks, can that be shown formally to can we show a provable gap between neural networks and kernel methods that relies on having to learn the features. And of course, ours is not the only work in this direction. There have been other works, but I'll mention some comparisons and contrast with those works as we go on. And we were also motivated by, we wanted to do this under sort of, it's still a simple setup, but it's inspired by some natural inputs, right, on which neural networks have shown great performance. So we wanted to focus one on classification setting where neural networks are really, right, the workhorse now, right, at least for large data settings. And also something, our natural inputs we look at are images, which is again, the use case domain that has seen most promise from neural networks. So what do I mean by, what is the aspect of natural images we are trying to exploit? So it's the fact that in natural images, when you're doing classification, the object of interest tends to be localized, right? And we call it a signal. So signal is essentially this set of label determining features, right? So for example, here are some natural images from the ImageNet, and you can see that, the label, if it's a bus, for example, in this image down, at the bottom left, then you can see that there's a localized patch, right, or set of patches that characterizes the bus, and then everything else is sort of like noisy background, essentially, right? It's not necessarily noise in the sense that it's, stochastic and zero mean, but it's like some pattern, right, that's not relevant, essentially, to the class that's assigned or the label that's assigned to this image. So this is the key property we want to exploit, that there are localized patches or signals and images that determine the label, and all the other patches are not relevant to the label. And can we exploit that and show something about learnability of this patch, right, that will help us prove that neural networks are actually better than any fixed mapping that you can learn. So one other, I guess, evidence in this direction that something like this localization effect of patches is happening is evident in results that report sparsity of neural networks, which are trained on natural images. So there has been a bunch of work, right, that has come up, which talked about how when neural networks are trained, right, they can either be pre-processed, or if you look at them, they tend to have a lot of zero weights, essentially, right, which basically implies sparsity. And here we actually did an experiment just to bring out this thing where we looked we trained a wide res net, right, on CFAR10. And this is just showing for different layers, right, as training progresses, how the number of active neurons or non-zero neurons, what do that look like? And you see that it drops very sharply for many of the layers. So there is an inherent sparsity that's going on, and essentially sparsity of the weights implies that there's selection that's happening on the input signal, right? Certain patches of the images are not propagating further, right? Others might be. So this is just to say at a high level that sparsity of NNs also supports this idea that there might be localization that's at play in why neural networks work better. All right, so the takeaway sort of message here, without going into any of the math, which we will get to in a little bit, is that we show that a small convolutional neural network trained using standard stochastic gradient descent from random initialization can, in polynomial time and sample complexity, find a local signal that's embedded, or a local patch that's embedded in this image, and threshold out background noise, particularly for classification. Right? And the corresponding lower bound would be that if we look at the corresponding convolutional neural tangent kernel, then it would require a much larger model, more number of filters essentially, right? Or more features, many more features it will need to extract in order to be able to accomplish the same task. Okay. So I hope this high level message, at least makes sense. We will ground it in specific model and write like what the specific results look like. Okay, so yeah, just to lay out the rest of the talk, I'll mention first some contrasts with existing work. In what ways is our setup different? Because of course there have been other papers that have also shown gaps between neural networks and kernels. I'll describe the setup then, which is exactly this model class of localized signals, and also highlight the high noise setting. So it turns out that this is an important aspect. It relates to how the different parameters in our model scale, how the image size, the patch size, and the noise scale with respect to each other. Because for some settings of these, the problem is just linearly separable, right? Or can be solved using fixed features. But there are, especially the higher noise settings, where you actually see this benefit of neural networks adaptive feature learning. And this is the idea we wanted to highlight, the denoising effect of neural networks in identifying localized signals. And then I'll go into a little bit more detail on the specific upper bound for convolutional neural networks that I talked about, and a corresponding lower bound on the convolutional neural tangent kernel, which corresponds to the same architecture. And finally, I'll present experiments which also support the hypothesis that we have, that as long as you make it like a high noise sort of setting where there's a lot of background and a small localized signal, right, we'll be able to show a gap between both the finite width and the infinite width NTK with respect to the corresponding neural network. And then I'll mention some open problems that our analysis does not handle. Okay, so just with respect to the literature, right, and looking at, in particular, focusing on literature that looks at this gap between neural networks versus kernels. So there has been a bunch of work which talks about approximation theoretic gap, saying that there are functions which can be approximated well by neural networks, but cannot be approximated by kernels. They, of course, bring home this idea of how many, weights, layers, neurons, etc. you would need, right? And how that's a more parsimonious representation when you do it via neural networks as opposed to kernels, but they don't focus on the learnability aspect. So we want to focus on not just the polynomial sample complexity, which you could get with an approximation theoretic argument, but also the polynomial time learnability. Then there is a bunch of work which focuses on regression specifically. And our goal was to think about the problem in a classification setting, which is more natural because that's where you see a lot of the gains, but also there are interesting twists as far as like, it's easier to prove things in particular lower bounds also for regression settings, but proving it for classifications. Is there a question? Okay, looks like not. But yeah, if there is one, please feel free to stop me at any point. Yeah, I'm fine not sticking to the, and I don't have as many slides, so I think we should have time for interruptions. Okay, so then I wanted to mention that, of course, there is at least one work that we are aware of, which does focus on classification settings and in particular looks at hinge laws. I'll say a little bit more about this work because it's connected to the next point, which is that some papers have looked at showing a gap between kernels and neural networks when you're when the signal, right, or whatever you're trying to learn is a hidden subspace. Okay, and both the paper I talked about on hinge loss classification by Danieli, as well as Gorbani et al. Paper, they both have this setup, but in their cases, the hidden subspace is fixed. Okay, but once you learn this, so you identify a fixed subspace, and once you identify it, you can show a separation. In our case, the subspace can actually move around. Okay, so it's about finding where this subspace is in addition to exactly what it is, right? Both pieces are important, as I mentioned. So it's not a fixed subspace, that's the main aspect. And then with respect to lower bounds, so there are two types of lower bounds essentially that people have shown in literature. One of them is showing a gap, right, or the limitations of any kernel, any fixed feature mapping essentially. And these are much harder to come by. And especially for classification, right? None of them exist. It's mostly again in the regression kind of setup that you can show this. So saying that neural networks are more powerful than any fixed linear mapping, that a kernel can bring. The other set of results are showing a lower bound or a separation between neural networks over neural tangent kernels. And our lower bound will align more with this second line of work where we show a gap between a CNN and its corresponding CNTK. Okay, but it is in a classification setup, and I think the challenge ideally you would like to get a bound of the former form that it's with respect to any fixed feature mapping, but that is much harder in classification because there are known provable computational complexity issues that pop up there. Okay, so then maybe to get the setup concrete, we are going to consider, and again, this is motivated by that there's a small patch that is the label determining, which we call the signal patch, and all the other patches are background, right? And we do look at it under a following generative model where your one of the rows, so xi is your input image, and one of its patches, I should say, rather than row, one of the patches has a W star pattern, which says what the signal pattern is, right? Characterizes the signal, and it's multiplied by y to say we're just considering a binary classification setting, so y will be like -1 or +1. Okay, so you either have W star in some unknown patch or it's -W star, and that's deciding your label. And everything else has IID Gaussian noise. Now, this part can actually be extended to consider other noise models as long as the projection, right? You can control the projection of whatever is off W star in the other patches, right? How much it aligns with W star. So as long as that can be controlled, there is a potential extension, but I'll present the results and we have only worked it out in detail for the Gaussian setting. So to set up some more problem parameters, the signal, right, which I'll call this W star, which is a single patch, is d-dimensional, right? And there are going to be k such patches in the image. Okay, so k patches, d is the size of a single patch. So overall, the image is k times d-dimensional. And the problem parameters are essentially then k, d, and sigma, which is the amount of noise. And the specific setting we'll focus on is that both the dimension of the patch and the number of patches scale with sigma. And I'll mention next why that's important. Okay, but I hope that this setup is clear because this is Again, it's a twice setup, but it's inspired by the fact that natural images tend to have localized patches that are indicative of this of the label. All right, so yeah, why do we focus on this scaling of high noise setting? So I'll mention both how K scales with sigma and then the relation of E and sigma. So, and sigma is the noise variance. So if we look at the low noise setting where sigma is order 1 over root K, then it turns out that setup is actually linearly separable, right? So you can use a convolutional linear classifier, right? Because all you're doing in that case is say, right, you know the exact W star, then you're just matching each of the patches. And now it's like you have K IID Gaussians essentially, right? And you're trying to detect, which class it might be. And but that can be done as long as the noise is not too large, as long as, right, because totally you're accumulating K times sigma square as the overall noise. Your signal is order 1, so then you can separate it if the noise is smaller. So in fact, there is another paper which has looked at a similar noise model or a similar setup, but they only showed results under the sort of low noise setting, which is actually what there is no separation in that case. So the high noise setting is really what is of interest here, because that is what makes the problem not linearly separable. So we focus on the noise variance scaling as log K over root K. So our results will be in this setup, though of course you can extend it to even higher noise. We did not explore the limits of how high you can make the noise variance, but even showing it for something like log K over root K is interesting because we know clearly it's not linearly separable in this case, right? And the key is that in this high noise setting, we actually need to, you can't do this global aggregation, which is what the previous convolutional linear classifier was doing, right? It was just W star, you match it up. Here, you actually need to localize the signal patch before you can aggregate this noise, right? The K times sigma square I talked about was coming because you could just aggregate the noise and the signal across all of the patches. So in this case, we first need to find that signal and only then do some aggregation. Now, a similar issue comes up as far as the scaling of each individual patch, or D, which is the dimension of the signal, with respect to noise. Because if D is a constant, right, then it's basically, imagine D equal to 1, right? Then it's just a sparse signal. We have, right, some coordinate that's, containing the signal. Everything else is Gaussian noise. So people in signal processing and so on have looked at the setting, right? It's just a sparse setting, and it can be handled with, fixed features like the random Fourier features, right? So they are incoherent with such a sparsity basis, right? As sparse spaces and random Fourier features are incoherent, so you can actually do it. So D equal to constant is also easy. And we focus on the high noise setting where sigma square can be bigger than 1 by D, because that actually requires you to learn the features. You don't know what is the basis in which you're actually sparse, right? It's not just the canonical basis anymore, right? So you can almost think of it, if you're coming from a signal processing background, this is a group sparsity setting, right? And we need to know the groups are not just constants, right? They're characterized by this W star as the pattern. And we need to be able to identify that to say, right, here is the basis in which you are actually sparse. So this actually has some connections to dictionary learning as well, right? Where you can think about learning this W star, the signal pattern, as trying to learn this dictionary in which things are sparse, right? And this is exactly where you would require, learning the features, and hence, right, we can hope for a separation in this setup. Okay, so then going on to, I hope that made sense, right? The scalings, right, why they are important. And then moving on to the setup where we use a very simple convolutional neural networks, as you probably have guessed, something that sort of does soft thresholding essentially. So we use ReLUs for that. And there are, I guess, 2 ways you can interpret it. The structure I've shown here, so x1 through xk plus 1 are basically just the different patches. And I guess we went to k plus 1. We are calling one of them the signal and k noise patches, but it's order k or k plus 1. Yeah, it's not a big difference. Yep. So here are the different patches. W is the convolutional filter that we are going to use. So either you can interpret our convolutional neural architecture as using a W and a minus W to filters for every patch, and then just applying those filters and combining their weights, right, to get to our prediction. Or you can also think of it alternatively as taking your original patches and then applying a weight W to those, and then passing it through a nonlinearity, which looks like the difference of the 2 values. right? So in the previous case, there was a single ReLU at each node. Here, you've just combined them, right? They're equivalent notions. And the second layer is sort of fixed, right? Or the final output layer, I should say. So it's all fixed at +1, or the other case, it's plus and minus 1. And really what we'll exploit is the fact that, right, ReLU leads to the soft thresholding, right? The specific combination of the ReLUs implies that everything that's between B and minus B, so right, B is the constant weight in the linear combination, that's going to act as a threshold. And everything between it is going to be set to 0, and outside of it, the ReLU grows in a standard way. All right. So this is what will enable the denoising argument to be made once you've identified the signal. All right, so some other things about the setup. So we assume logistic loss, right? Because we want to focus on classification. So this is the standard cross entropy sort of loss, right? We'll consider the logistic one, and we focus on mini batch stochastic gradient descent. This is all standard, but I'll just mention it here to highlight a few things. So we initialize, what we are learning are all the W's and the B's, which characterize our filters, right? So we are going to initialize them to just be Gaussian with a small variance. So here the noise variance sigma naught is essentially 1 over poly k. K is the number of patches. Okay. And the learning rates, that's another thing I want to mention. So there's going to be a learning rate for B and a learning rate for W. Both of those are going to be, again, inversely 1 over poly k. I wanted to mention that we actually chose the learning rate for B to be lower order than the learning rate for W. Now, in practice, this doesn't usually happen, but this helps simplify the analysis, because then we can essentially focus on the learning rate for W is bigger. So we can talk about what happens to W first. How do we learn to identify the signal pattern? And then B kicks in after that, where B is going to act as the threshold, as I explained on the previous slide, right? So it's just about like when W aligns with W star, which is our true signal pattern, and then the thresholding kicks in. And then the only other pieces, it's we do the mini batch version, where every batch is a poly k, again using poly k number of samples. You compute just your empirical gradients and take a step in the stochastic gradient sort of way, right? So why choose them? Yes, please go ahead.
I was just wondering, so would you relate this to like something like the reweighted L1 type of optimization, right? So you're going from like a lasso procedure to something that you're updating the threshold weights on the fly.
We have not made that connection. That's an interesting observation, right? Yeah, that we could try to think about, how so we haven't showed any reduction from, like, here B is just like acting like this threshold. You're right, it is a soft threshold. Maybe we should think about, but we haven't explored that. Yeah.
Thank you.
So yeah, that's a great question. Yeah, maybe there's a way to think of it as like reweighting is actually, enabling that effect. Yeah, so the reason we chose a mini batch is just because that allows us to focus on the population gradient as opposed to the sample gradients, right? So saying that there's a batch available at every iteration, right, implies that with high probability, the sample and the population gradients are close to each other. And then the only other thing is, for getting into it, is the stopping time. So we say that stopping time t is basically when the probability of error falls below 0.01. Or for all times before it, the probability of error is above 0.01, which is just the target accuracy we aim for. Okay. So what does the sketch look like for the upper bound? Well, we're going to learn the signal pattern, as I said, that we chose the learning rates to be slightly different to help break down the analysis into these two pieces. We're going to show that our learned W, which are the neural network convolutional filter weights, align with the signal pattern W star. This dot product between W and W stars keeps on growing, because the gradient of the loss we'll show is actually going to be large and negative, right? So at least theta 1, and that will imply, right, a negative large gradient implies the alignment between the learned filter and the actual signal pattern will keep on increasing. And then thresholding then kicks in, where our threshold B is going to grow. Here, the gradient is once again of the loss with respect to B will show as large and positive, right? So B actually is the negative of the negative of B is the threshold you're actually applying in this case. So yeah, it will also grow, but it's going to grow negatively. And then because every step size, all the step sizes are polynomial in K, we can achieve high classification accuracy. We'll show that it only takes poly K iterations to do that, and hence the sample complexity is also going to be poly K. Okay. So actually, before going into details of some of these aspects, I just wanted to mention a simulated empirical result, right? Show that and to highlight the 2 points I mentioned. So here we can see that as SGT steps increases, right, we have a specific setting of K being 1000, D is 10, which is the single patch size, and 1000 such patches, noise variance fixed to 1, and the learning rates, as I said, differ by a factor of K. So 0.1 and 0.1 over 1000. And what we see is, so the top thing is exactly this alignment of the learned filter with the signal pattern, and that keeps on growing as the steps progress. And B, which is the negative of the threshold, also keeps on growing, just grows negatively. And it's the ratio of these two that's actually the driving factor, right? So how much is this is like the signal to noise ratio effectively. B is the level at which we are thresholding. W dot W star is the amount of signal. And we see that as we are able to threshold, right, more and more, this pattern aligns with the test accuracy then that we see. That also keeps growing up. Okay. So then to maybe get into a little bit more detail, we can talk about exactly how the analysis progresses. So we are going to look at, as I said, the population gradient, right? We get rid of the sample part because we just assume poly K at every step. So this is the population gradient of the loss and how it aligns, right? How does it look like along the true signal direction? So we look at it along the signal direction and then off the signal direction, and then do similarly for the gradient with respect to B. So here we can show that the signal patches contribution is essentially negative constant. So W star has unit norm, right? So we fix that. So that's a constant, and that implies that the signal patch just contributes a large negative value to it. The noise patches contribution grows. It grows with number of patches, amount of noise, and also actually this level of alignment that the filter has been able to achieve with W star. So this is where having a different step size also comes in, because as long as the alignment between our current filter weights and the signal pattern is not too large, which is the case in the initial stages, as long as it's not too large, we know that the noise patches contribution is controlled. It's not also growing too large for the specific high noise setting, right? You see the product of K and sigma square coming up here. This is, again, saying that this will scale if the noise is large, but then as long as we haven't aligned well with the direction as much, the signal patch is the main contributor and keeps driving the gradient of the loss with respect to W along this direction to be a large negative number. Then we can look at the non-signal direction, which is basically the perpendicular direction, right? And along this case, we can show signal patch doesn't have any contribution, right? The noise patch contributes here, but the amount of how much it contributes depends on essentially the norm of this W perp vector times, again, the remaining things, which are, again, in the high noise setting, right? They scale accordingly. And we're going to show that the gradient of the loss with respect to W along the non-signal direction, it is going to be, oops, I think it looks like I'm missing something here, or at least, yeah. But I think it's all the only thing that matters is it's positive, but it's which causes non-W2 to shrink, right? A positive gradient implies the norm will shrink. So W perp will not grow too much. The signal, our W vector, the filter, convolutional filter, will keep aligning with the signal pattern, while in the orthogonal direction, it's going to shrink. That's just a shot here. And then for the threshold, similarly, we can look at the population gradient of the loss with respect to B. And in this case, we see that the signal patch contribution is large negative or constant. And the noise patches contribution is this quantity, which depends on, again, how well the signal has learned the signal direction, and then something that's like K to the 1/8. This is where I think this can actually be, there is some looseness in our bounds. So this can actually, I mean, it works for our setup, but it can actually improving this, or actually doing a more formal analysis of tracking sigma. So we have assumed sigma just scales like log K over root K, but you can actually make sigma larger. And we can see this already because of this gap that's showing up. We have K to the 1/8 where we all we care about is it should be like log k, essentially, some factor of log k. But anyway, this works. So for any t where you haven't achieved the good accuracy yet, this amount of alignment is again controlled, and hence the gradient of the loss with respect to b is right. Once it has reached this 1 over k to the 1/8 level, right, the gradient of the loss with respect to b is going to be a constant, and it's positive, which means it's going to cause b to decrease and be large and negative, right? So it is interesting that it's not that b is always decreasing. Actually, if you zoom in on the plots I showed earlier, there's an initial phase where it can grow a little bit, but it doesn't grow too much, and then it starts decreasing after that. Okay, so these pieces let us put together the whole story. So the signal alignment of our learned filter with the true signal pattern, it grows to something like 1 over log 4k at a rate, right, which is essentially depending on the step size, right? And because the step size is polynomial, this only requires poly k iterations, right? We're asking it to grow from a small value to 1 over log 4k in poly k steps. So that works. And then for the threshold, that also increases. It increases at a rate of the step size corresponding to b. And it has to grow large enough so that it can match the largest noise that you will get along w. And how much is the largest noise along w? Well, it's just norm w times the max of k Gaussians, right? Max of k Gaussian scales as sigma square root log k, right? And along w, it can only grow to norm w times that. So as long as norm of w is controlled, right, the threshold will be able to increase past that. So we can see that for, right, all the iterations before this are the alignment, right, does not grow beyond order 1. We can show that of the true signal. And then in the perpendicular direction, we showed it actually decreases. In fact, it is kd over the initial variance, or sorry, kd times the initial variance, which is 1 over poly k, right? That was our initialization. So the norm w perp actually doesn't grow too much as well, right? Which controls the overall norm of w to no more than order 1. So along the signal direction, it can go to order 1. Along the off direction, it is shrinking, and hence the overall norm of w is only order 1, which means, right, you just need the threshold to grow to sigma root log k, which is the max of k Gaussians. Yep. So, and this also happens in poly k iterations, right? The threshold is growing for something with 0 all the way to sigma root log k, essentially, at a rate of eta b, which is poly k. So overall, it requires poly k iterations and just poly k samples at each step, which means the sample and computational complexity are both poly k. Okay, so I know that got a little technical, but hopefully made some sense as well, at least intuitively. And I also pointed out sort of like where there are, you can see that we only need the alignment to grow as 1 over log 4k, but in our analysis, there's a k to the 1/8, which is, so there's a huge space for improvement, but it's just saying like we can push the noise even higher and show a gap. So this gap still works at this just a log k worse noise than the linearly separable case, but we can go much higher. Okay, so then onto the neural tangent kernel lower bound. So we look at the neural tangent kernel corresponding to the convolutional neural network architecture we showed earlier. So specifically, it looks like as follows. So this convolutional neural tangent kernel, we allow it to use certain number of M filters, right? Yeah, this is just forming that linear combination. And then this part is just fixed, right? Because this is, again, a fixed kernel corresponding to the neural tangent kernel idea. So we allow any threshold B to be used here. And the WJ0 is whatever the random initialization would correspond to. Okay. And we look at, again, the high noise setting, because that is where there is a separation. So sigma is larger than log k over root k, and it grows as 1 over d as well, for the reasons I described earlier, that if d is a constant, then random Fourier features would work. So what we can show is the following, that as long as the number of filters, right, this M used is a constant, right? So in our upper bound construction, M was just 2. We're only using 2 filters, or 1 filter if you combine it together and don't think of it as a relevant, right? But here, if the number of filters are you can make it larger than 2, of course, but as long as they're a constant, right, then for all k that are above some threshold, right, then with high probability over the random initialization, for every set of weights and every set of any bias that you pick, the probability of error cannot go below 0.1. Okay, so it will stay above 0.1. And I won't go into the details of this, but yeah, this just has to do with the fact that, yeah, we're fixing the features that can be used here. So you can show this gap unless you're able to use a lot of features that scale somehow with K and D. So as long as if number of filters is not scaling with K, D, sigma, right, the problem parameters, this can't be achieved. Okay, so maybe to show some empirical results supporting this phenomena, we looked at a 10-layer wide ResNet, right, and CFAR 10 images to start with. So we wanted to mimic something which we want to be able to control the amount of noise essentially in our images, right? Because our whole theoretical premise here is that you're able to get better denoising using neural networks than with kernels because they're able to localize and find this patch effectively. So what we did was we scaled these images to 16 cross 16 and placed them on a bigger image, which is 32 by 32. So it's a 16 by 16 image placed over a bigger 32 by 32. And the background either had Gaussian noise or various types of noise, as I'll describe. And then we could vary the intensity of just the background pixels and look at the effect. So the first one is experiment is CFAR 10, as I said, with ImageNet as plants synset as the background. So that's the background. We put a little the 16 by 16 patch on top of it. And we can now vary the intensity of the background pixels. And we see that there is a big gap, which only gets bigger as the noise increases with respect to the corresponding neural tangent kernel in this case. And this holds true even if we reduce. So here earlier was CFAR 10, right? All classes. Here we only focus on 2 classes, animals versus vehicles. And the gap is narrower in this case, but it still holds even for a 2-class setting. And if you replace the background clutter, which the plants one is actually more natural with just Gaussian, you see a wider gap between the two. Right, so the theory was for the Gaussian setting, but it does work with general backgrounds as well. And here's yet another type of background where instead of having like a plant's background and then having these like animal objects or something in front, here what we did was we did vehicle categories with animal categories as the other remaining patches. So the goal here is to identify 4 vehicle categories and the vehicle is in one of the patch, but then the remaining patches are taken from some animal category. Okay, and they are just found. So basically these patches are the ones that should not determine the label, but they are highly structured as opposed to Gaussian noise. And we still see that this big gap preserves between, CNN and its corresponding, or in this case, wide ResNet CNN and its corresponding NTK. Now, one question that came up was our theory as well as experiments so far were with a finite width NTK. And of course, the infinite width is supposed to be more powerful. So does the performance actually degrade if, right, or this gap closes if infinite width NTK is used? And the answer is, so here, infinite width is harder to implement. We were not able to do it on very large data sets. So initially we did it, we did the infinite width only for MNIST with a 20,000 subsample of the MNIST data set. But we can still show that despite going to larger width, yes, the performance improves over the finite width, but you still have this big gap, especially as the noise increases. And here are some other examples. This is on full MNIST, but we can only go to a width of like 100 here, but the gap is clearly there. So with that, I'll mention some open directions. As I mentioned, one is we consider our analysis and showed a separation for noise levels scaling like log K over root K, which is in the non-linearly separable setting. And similarly, the sparsity not being like group sparsities or noise, the dimension of each patch sort of scaling with the noise variance. And how large you can make it is open. We didn't investigate that. So we can actually show even bigger separation by pushing the noise thresholds up. We just don't know how much we can push them up. Other issues are, well, of course, going noise models beyond Gaussian. As I said, it's possible as long as you control the amount of projections, because that's basically what the whole analysis was based off of, but we haven't done it. What would really make it powerful is actually non-aligned. So right now our patch, right, signal is exactly aligned with, I mean, we are saying it can be in this patch or that patch, there's no overlaps allowed. But aligning it to be, yeah, non-aligned would be, with the convolution filters that are used, would be interesting. And then another thing is like, yeah, the lower bound, ideally showing it for all kernels, but it's hard to do that in the classification setup, especially showing a result of the form we have, right, which is on the accuracy. You can, of course, show other types of results, like sample complexity result might be possible, but, or a representation kind of result. Yep. And then, yeah, deeper networks. We didn't, of course, our setup only considers a very simple scenario, but potentially when we consider non-aligned patches, it seems like you might have to consider them at different resolutions, and that's where depth might play a role as well. So I think the third point and fifth point here like are sort of coupled with each other. All right, so that's it. Stephanie is my student who really worked on this, along with Ezra, who helped with a lot of the experiments, and Yuanzi is our collaborator, and this work will appear at NeurIPS 2021. So, yep, that's it. Thank you.
Awesome. Thank you so much, Aarti, for the great talk. We have about 15 minutes for questions, and I'm sure there are plenty. Raman would like to ask a question. Go ahead, Raman.
Yeah, so can you say a bit about what I mean, what gap are we talking about? Maybe it wasn't clear to me when I mean, are we talking about there being a statistical complexity gap between an algorithm that's tractable and another that's not? That's not quite that, right? I mean, I would imagine. I don't think CNT, you saying it's intractable in this setting. Can
like that
you
is computationally intractable? Yeah, so we did not convert it all the way to that, but what we do say is that you require more filters, right, essentially. So you would require more filters to do it with a kernel, whereas
so to guarantee some kind of packed learning guarantee, right? I mean, we can't drive the error down to arbitrary small epsilon, but what you showed is that error, if you don't use enough number of filters, the error is bounded from below by some constant 0.1, whatever, right?
Yep. Yeah.
So there is a gap in the I mean, so it's not learnable with CNTK. I mean, forget about I mean, I'm not even talking about runtimes. Are you saying that given any number of samples, forget number of features, forget runtime, no matter how many samples do I give you, this problem is not learnable through arbitrary error using a CNTK?
Yes, true, except I'll remove the number of feature part from what we just said, because that is limited by the number of filters, right? We are saying as long as you are limiting the number of filters to be no more than a constant, right?
So that's, yeah, okay. So that's the part I wanted to get to. So then this is a gap between the statistical complexity of two learning rules, right? I mean, you basically saying given this sample size, I cannot learn this using a CNTK, right? I mean, it's
given this many features, you cannot learn it, right? Basically.
But you just said number of samples is related to number of features.
Is
right?
right. Yes, exactly.
So I mean, I'm trying to see in what sense is there a gap? Usually when we talk about gap, we basically say, oh, there's a gap between statistical complexity for an algorithm that's tractable versus intractable, right? So we're creating some kind of a computation.
Yeah, so you can say it is a sample complexity gap. You can say that, right? But I think, yeah, exactly. If you wanted to make it exactly a computational gap, that is hard in the classification setup, just because, right, you can't.
No, I'm okay with the statistical complexity gap. I just wanted to understand. But it's a statistical complexity gap between two rules, but they're not necessarily one is tractable and the other is intractable. We're not saying that.
So yeah, I mean, what we are saying is one is polylearnable, the other is not learnable with fixed. I mean, I know it's a twist on the same thing, but yes, it's not formally showing that, yeah, how many.
Yeah, if it's not poly time, if it's not learnable by poly sample, it's not learnable by poly time.
I'll be happy to follow up on another question, Aarti. So actually, I have a couple of questions. The first one is when you were talking about not perfect overlaps between the filters and the patches, are you? I'm curious what the main difficulty there is, and perhaps is the difficulty the fact that now the samples that you see, that the inner products are not now independent?
Yes, exactly, right? So, and you also have to like, so yeah, one is that they are not independent, and other is you have to like think about what fraction of it is captured by each, right? Depending on how big your signal is, yeah.
And
So
then,
no, go
yeah,
ahead.
and your hope is that if you look at this at a low enough resolution, then things will eventually become independent because it's just the resolution beyond one, right?
By low enough resolution, you'll.
Excuse me,
I
but
think what we are assuming is that the filters are aligned with the signal patch, basically, right? So yeah.
yes,
So yeah, okay, maybe that's what you mean. That if you look at a low enough signal, you will capture the signal in a few non-overlapping patches. Right?
exactly,
Yeah,
exactly.
yeah, that's a good way to say it. But I guess, yeah, I mean, yes, though I think then you should also think about how many patches your signal is occupying, and if that scales in some way, that also will play a role, right?
Right, right.
Yeah.
And I'm curious about your, so you talked, and also the empirical results, I think they were all in the setting of binary classification. And I'm curious what the main difficulty is for extending this to multi-class settings. I would assume that things remain more or less the same, except now you need to include some assumption about the correlation between the filters of the different classes.
Yeah, no, I think that is probably a simpler extension. I mean, yeah, you have to like think about span, right? Of you'll have a different W star characterizing each class, and then yeah, I think that's more possible than the non aligned one.
For sure, for sure, for sure.
Yeah. Yep, exactly.
Terrific. Are there any questions from the any of the panelists or the attendees? Oh yes, I think Raman wants to follow up.
Yeah, if I can, I mean,
Of course, of course.
So I mean, I'm a little still the same question in a different way. So I mean, one way perhaps, or maybe a comment, well, maybe one way to think about this is perhaps that there's really a gap in approximation. No, I mean, I have a hypothesis class which can efficiently capture the reality that I have here, and it's not, you know, it's, I mean, it's there is a strong assumption about reality also. We should acknowledge that. But you know, one way to think about it is I have a hypothesis class which captures the reality with, you know, few number of parameters, and you know, there's another hypothesis class where I will need many more parameters, and somehow here samples are being tied to the number of parameters, right? So I mean, either I try to decouple them, number of samples with the number of parameters, right? Or I argue that there is a gap in terms of approximation, right? How well can I capture this reality, approximate this reality, given certain bound on the number of parameters? I mean, is this another way to think about this? I mean, I know, I mean, they're related, you know, and maybe a more interesting takeaway here is that the statistical complexity gaps, or even you know, computational complexity gaps, but wouldn't that also be a reasonable takeaway from this, that, you know, there's the reason they follow is because there is essentially a gap in terms of what the two hypothesis classes can represent about this assumption that I made about reality.
So yes, you are right that it is, of course, this does imply that there is an approximation gap as well, right? That, yep, neural networks are able to represent it. But of course, as well, okay, so just to make sure, when we say that, we're taking noise into account, right? So represent it well, given the amount of noise, because otherwise you could do it, yeah. But yes, there is an approximation theoretic gap. And on top of that, I guess we show learnability, use at least in polynomial time, using neural networks. So that's a fine takeaway, I think, as well. Right, that there's a sample complexity gap, which is coming from approximation gap, but there's also learnability of the, right, of the function by neural networks that accompanies it. It's not just
What I'm
that
trying to
you can approximate with some infinite power, right? We can show that you can, in polytime, approximate it with neural networks. But we don't have a computational statement for the lower bound. That's what I think you're getting at. Yes, or so.
I mean,
Yeah,
I'm
we can
trying
talk about
to.
it more.
Yeah, we can talk about it more.
Okay, there's one question from the attendees. This person asks, could you comment on how the gap you showed for the CNTK is related to the generalization error bound of the neural tangent kernel? For example, how classification target is aligned with the NTK spectrum?
I think I did not follow the question. Can you say it again, maybe slowly?
Yes. The question is, could you comment on how the gap you showed for the CNTK is related to the generalization error bound of the NTK? And as an example, how classification target is aligned with the NTK spectrum? Maybe we can also ask whomever asked this question to maybe clarify and follow up.
Yeah, I guess I'm confused about, like, are they thinking about, okay, what the infinite NTK is? First of all, do they have infinite NTK versus finite? So our lower bound is for the corresponding CNTK, which is finite
Right.
width. Are they asking about the corresponding infinite width NTK and its generalization ability? Yeah, if the person can clarify, that would be great.
While this person hopefully clarifies on that question, can I ask you a little bit more on what you mentioned before, in particular related to these works that analyze similar gaps in cases where samples are drawn from some low-dimensional subspace? And you were mentioning that in this case, the subspace is variable in some sense. Could you explain that further? It wasn't totally clear to me.
Yeah, so because the signal patch can move around, right? Even for the same class, it can occur in any of the patches. That's equivalent to a non-fixed subspace, right? A fixed subspace would be, at least the one that's, for example, considered in Daniele et al. Paper. They have a vector, and then a part of that vector has a fixed part, has some parity pattern, right? Or something like that. But it's a fixed part of that vector. So it's equivalent to fixing the patch. So that's what I meant, like here, the patch can actually move around. And we could make it, again, we assume that the signal pattern in each patch is just like a W star vector. It could actually be a D-dimensional thing, right? We only have we're only spanning a single dimension within that. So you can enrich it even within a single patch. And that will also lead to, I think, more powerful results.
I see.
And I think it ties to the multiclass question. Right? In multiclass, you would have to do that anyways, right? That you can have multiple vectors corresponding to each class.
Correct. Okay, so if there are no further questions, we can go to a 5-minute break and we will resume at 1:20 Eastern time. And then if this person wants to clarify and comment further on the question, Aarti, you will be able to also answer the question on the Q&A by typing your answer if you would like to stay.
Sure, sounds good.
So we'll take a 5-minute break and resume at 1:20.
Thank you.
Thank you so much, Aarti. Okay, so welcome back, everybody. We will move on to the second part of the second session. We have 2 contributed talks. First, we will have Blake Bordelon, who is a PhD student in the applied math department at Harvard, working with Cengiz Pehlevan. His research interests are in the intersection of machine learning, statistical physics, and theoretical neuroscience. And he's going to tell us about stochastic gradient descent on structure features. Blake, thank you so much for your contributed talk. Looking forward to hearing it.
Yeah, thank you so much for the great introduction, and thanks for giving me an opportunity. to speak a little bit about this. So I probably don't need to convince all of you that stochastic gradient descent is an important algorithm to understand, given that it's sort of now serving as the foundation of modern machine learning, especially deep learning. And its performance, this algorithm's performance, obviously depends on a variety of factors in the learning problem, including the structure of the data, the structure of the learning problem that I'm trying to actually solve, the architecture that I choose, right, the type of model that I stipulate, and then the hyperparameters that I set. So things like choices of learning rate or batch size in the case of SGD. But a fundamental, okay, in this talk, basically I want to develop or discuss an average case analysis of SGD in a model that's simple enough to be solvable, but that still captures at least some degree of all of these different dependencies. So we can see how playing with feature structure, models, or the different hyperparameters can control how fast you learn during SGD. So first, I just want to kind of convince you that the structure of the learning problem, the data itself, really matters in controlling the speed of how quickly you can estimate some ground truth target function. So here I'm going to think about basically 3 different learning problems, but all of them will use essentially the same model. So I'm going to use a ReLU random feature model, which essentially projects my my input data through a random Gaussian matrix G, applies some element-wise nonlinearity. And then I'm essentially only going to train these weights in the second layer, these W's. So you could think about this as a 2-layer neural network where I only train the last layer weights. And I'm going to compare basically the performance of SGD. So this LT will be the test risk during SGD as a function of the number of iterations for MNIST, CFAR, and random Gaussian vectors in the same dimension as MNIST. And so here I'm going to keep the algorithm the same, the SGD will be the same, and the random feature model will be the same. But you can see that the learning curves are very different. So is there some way that we can rationalize why the structure of the data is driving such different performances for the same model? So in this setup, I want to think about the simplest possible model to solve, right? So we can get some intuition about the nature of SGD. So I'm going to just stick with MSE loss for analytic convenience, and I'm going to basically think about models of the form that I was just describing. So I'm essentially working in like the kernel regime. I think about a feature map psi of x, potentially nonlinear, that maps my data to some possibly high dimensional space, and the trainable or learnable parameters in the model will just be these weights W. So the model itself is linear in the trainable parameters, but nonlinear in the data. I will assume that basically all of my data points are drawn from some distribution P of x. The parameters are, the trainable parameters are W. The model, so by changing the feature map, it's sort of like an analogy to changing the structure of the model, and then the task or the target function I'm trying to approximate is this y of x. And you can sort of easily calculate what the sort of SGD update is. So if this is my population risk, which computes the average over the full population distribution P of x, I can approximate this by taking samples, x mu t. So at each time t, I draw a mini batch of size m, and I use this mini batch to sort of compute a stochastic gradient estimate. And so what's interesting about this dynamics is that after t steps of this process, my parameters and my test loss will actually be random variables because they'll depend on the random history of samples that I've drawn up to time t. So because this test loss is a random variable, I mean, I want basically some scalar quantification of this random variable. So the simplest thing you could try to do is basically compute its average. So I want to basically develop a theory that lets me average over the history of all observed samples up to time t and obtain this sort of what's called the learning curve. So there's a one-pass interpretation of this. So if P of x is some distribution, some arbitrary kind of test distribution, not just on finitely many examples, I could interpret LT as the expected test loss, and where basically at each time step I'm drawing m fresh samples from the data distribution. But you can also reinterpret this in terms of a multiple pass setting, where you think about a fixed training set of size capital M, and I think at each time step I sample with replacement uniformly from a uniform distribution on this set of examples. And in this case, the LT will actually represent the training error. But if you stipulate some new test distribution, you can also within this framework calculate the test error curve in this setting. And if you're interested in more about this, please come by our poster or check out our preprint on archive. So I'm going to now sort of state the result. So basically the crucial thing in this setting is the feature correlations. So I basically just average this outer product of features over the data distribution. And then what's really going to matter is I need to diagonalize this matrix. So I need to find its eigenvalues and eigenvectors. And then I want to basically assume a square interval target function so that I can decompose y of x. This is the function I'm trying to approximate. I can decompose it basically in terms of something that's learnable in the features and some component that's unlearnable, which will lead to some irreducible loss. And I'm going to essentially express these, optimal weights W star in the basis of eigenvectors. And then I'm going to calculate basically this irreducible variance, this variance I can't estimate with my features. And so I just want to state, I'm not going to give the result here, but you can actually solve this model exactly for the average expected loss over the history of samples in terms of second and fourth moments. But the second moment, for sort of sufficiently regular second moments or fourth moments, you can close everything in terms of the correlations themselves. And we can chat afterwards or a bit at the poster session if you're curious. But essentially, you can write the expected loss after t steps of SGD in terms of the eigenvalues lambda, these coefficients b, right, which are basically the projections of the optimal weights in the on the kth principal component, the unlearnable sort of quantity of variance in the target function, learning rate, batch size, and so the time dependence comes through this matrix power, this matrix A to the power T. So this is the complete result. And the above formulas are approximate for non-Gaussian features that are sufficiently regular, but it's actually exact for Gaussian features. So if your fourth cumulants vanish, then this is the exact result. So can we give an interpretation of this result? So we showed that this expected loss basically depends on time through this matrix A, and this matrix A has two components. And so the first is probably familiar. This is just diagonal matrix, and it's just essentially defines how your loss would evolve if you were just doing population gradient descent. And you can see that by taking m, the mini batch size, to infinity. So if I took the mini batch size to infinity, my fluctuations in my gradients disappear, and I'm essentially doing gradient descent on the population risk itself. But this term is actually comes about because of the gradient noise. So the fact that because I'm sampling random data points at each step and computing a noisy gradient estimate, I get this additional factor. And you can control it by increasing the mini batch size. What's interesting is that because this matrix, this last term is non-diagonal, this is actually like a consequence of the fact that the gradients correlation matrices and the feature correlations don't commute throughout gradient descent. And this will actually have consequences for what what batch sizes are optimal, for example. So I'll talk about that later in the talk. So just to sort of verify that this works, I'm going to show that same example I showed early in the talk, where you take the eigenvalue, but I'm going to show basically how you get these theory curves, these dashed black curves. So you obtain these theory curves by basically calculating the feature correlation eigenvalues lambda k for each of these different data sets, or each of these different sort of features. So you take the data, you pass it through the feature map, you calculate the lambda k's, and then subsequently you also need to calculate the sort of decomposition of the task function y of x in that basis. And so these two numbers, uniquely determine these average learning curves, these black dash curves. And so this is just a verification showing that this works. Is there an exactly solvable case that gives us some intuition? So there is. If in the case where your features are completely unstructured and all eigenvalues are equal, this is a model that was studied by these authors, Werfel and colleagues in this earlier work. And here you get basically exponential convergence, but with a time constant that will depend on the ambient dimension. So regardless of what task I choose, regardless of what my target function is, I will always sort of suffer the same time complexity. I need at least t on the order of n steps. And so here I'm here in this plot, there's the same target function, but all I'm doing is just increasing kind of the dimension of my feature space, but maintaining this isotropy in the feature space. And you see that it takes longer and longer time to learn the same function with higher dimensional features. So this is just the classic kind of curse of dimensionality, hard to learn in high dimension sort of thing. But I think a more realistic model of data is one where, in those previous plots, I was showing that the real feature eigenvalue spectra were falling. They weren't sort of constant for all index, right? So I'm going to stipulate maybe a simpler toy model, which is maybe they're falling some power loss, some k to the minus b for the eigenvalues, and then the amount of power in mode k for the target function might decay k to the minus a. So in this setting, you can show that at large time, you should essentially get a power law scaling in your expected loss with a certain exponent. And this has been calculated in other works. I'm not claiming this is completely novel. But what's interesting is that this is actually sort of insensitive to the ambient dimension. So even as I make the sort of ambient dimension go to infinity, I'll still obtain this rate. So even in infinitely high dimensions, I can still learn, provided my features have structure. So I just want to argue that the real case where I actually train on structured data is more like this case than the case where I stipulate isotropically distributed vectors in high dimension, which is, so for instance, if I take MNIST data and I just whiten it or something, I get this like essentially this green curve rather than this blue curve. So the structure of data really matters. How far can you push this? Do these power laws, are they descriptive in more realistic settings? So up to this point, I've talked a lot about random feature models. What if I train the network end to end? So still wanting to work within this lazy limit, I'm going to think about, I guess, neural networks with NTK parameterization that are sufficiently wide so that basically I can describe them as learning a linear model with a feature map that is just essentially the initial parameter gradient of the network function. So this is the NTK limit. And what's interesting is it actually, this SGD theory is actually kind of descriptive in this case. So these are not super wide, but they're like sufficiently wide with 500 multi-layer perceptrons of varying depth on MNIST. And all I'm plotting here, I'm not plotting the full theory, I'm just plotting a predicted power law scaling at large time. So those exponents that I calculated in the previous slide, I'm plotting them here against the experiment for different depth multi-layer perceptrons. And even more sort of like, even more dramatic is the difference in the predicted exponents for like convolutional models versus multi-layer perceptrons on CFAR. So here you can see that like at large time, I'm getting a much better decay rate for my convolutional sort of neural tangent kernel features compared to the multi-layer perceptron features. But all of these things are just computable in terms of just, all I did was calculate the slopes of the eigenvalue plots and the slopes of the task power plots and then predict an exponent here. So it's actually like kind of nice, at least in the lazy learning limit, you can get some prediction. So now I want to talk a bit about like choice of hyperparameters. So I told you that the features are maybe structured. What's the best way of choosing batch size or learning rate? So you need to define this problem properly, right? So if I fix the number of iterations, if I fix the number of steps t, then you can prove that the expected loss will always get better if I make the batch size bigger and bigger. And that's just because I'm getting cleaner and clearer gradients that are approaching sort of the real gradients of the population risk. But this is not the appropriate comparison. The appropriate comparison is actually to, well, why is it not appropriate? So if I increase the batch size by keeping the iterations fixed, I'm seeing a large number of samples, and I'm consequently also just like taking a large number of gradient evaluations. So I'm using more compute, I'm using more data. So the fair comparison, which was discussed very clearly in this earlier work that you should check out if you're curious about this, is just you really want to fix the computer data budget, which would be really the product of number of steps and the batch size. And then ask, for this fixed compute budget, what is the best batch size to pick? And intuitively, what this means is it's trading off taking a larger number of steps with noisier gradients, or sort of taking fewer steps with very clean gradients that are like approximating the population risk really, really cleanly. So you can do this, since we have an analytic theory, you could plot these curves at fixed compute, and you could ask, what M should I pick? So I do this for different like types of features, and generally the optimal batch size is small. So unlike at fixed t, the optimal batch size is infinity, and if you fix the compute budget, generally the batch size is small. For isotropic features, it's generally close to 1. Like lower M is better. But for structured power law features, there can be intermediate optimal batch sizes, but they're still very small. I want to stress this is less than 10, right? So these are still very small batch sizes. And you could ask, how should this scale with feature structure? So as I change maybe the feature correlations, or I change the task, how should I pick the optimal batch size? So you can prove within this framework that the optimal batch size should scale with actually the sum of the squares of the feature eigenvalues. And this is a little bit surprising because it's not scaling with the total variance of your features. It's scaling with this interesting kind of intermediate quantity, and you can verify this scaling. So for example, for isotropic features, this would be basically just a sum of 1 squared for all n, however many dimensions you have. And for power law features, it's just this order 1 thing, even as I take the ambient dimension to infinity. Okay, so this is the last, I guess, technical slide. So here, what I'm plotting is for different learning rates, different batch sizes, what is the loss at a fixed compute budget C? So I think I picked here like C is 200 or something. And this is for a power law feature setting. So there's a region of instability where I can't learn because the learning rate's too large and the batch size is too small. So here the gradients are too noisy and my loss will diverge in expectation. For any sort of learning rate, I could ask, what is the optimal batch size? So if the learning rate, and that's this black dash curve. For sufficiently small learning rates, the gradients are already sort of pretty low noise. And so there's not much advantage to taking a larger batch size and sort of averaging. So in this regime, the best batch size is 1 because I want to take as many steps as possible with my fixed compute budget. However, after a certain critical learning rate, my gradients become noisy, and it's best to actually trade off number of steps for basically denoising my gradients. And you can see that along this region, the optimal batch size is like kind of hugging the stability boundary. And you could also ask if I wanted to optimize both parameters, so I want to optimize learning rate and batch size. The answer is actually in this corner, essentially. And approximately, basically, you need to scale the learning rate like with batch size like this. And then with this choice of learning rate scaling, the best batch size is to be as small as possible. So basically, the loss will always kind of increase with batch size. So this just shows basically the benefits of using very small batches if you've tuned your learning rates appropriately. So anyway, so in conclusion, the data, the model, the task, and your choice of hyperparameters will all matter during SGD. They'll all sort of collectively conspire to give you your sort of error curve. SGD on structured data behaves very differently than unstructured data. You need to basically remain stable by decreasing your learning rate compared to what learning rate you can choose in the population risk limit, or make the this should say larger. So if I make the batch size small, I need to also make the learning rate small to remain stable. The optimal M at fixed compute is really typically small, and all of the power law features and random feature models I mentioned, it was never bigger than 30. And it scales with the features through the sum of squares of eigenvalues. And so if I tune my learning rate appropriately, then small batches are always better at a fixed compute budget. So with that, sort of, if you're interested, come by, say hi at the poster session, and you can check out this paper. And just thanks to members of my lab for useful conversations, and thanks to funding. So I'm happy to take any questions if there's remaining time.
Awesome, thank you so much, Blake. We have time for 1 or 2 questions. And I'm going to be a little bit selfish and take one of them. So, Blake, you had a plot here where you basically sort of regressed the value of, I forget what the notation was, beta maybe, basically the power law scaling for MNIST. And I wanted to understand that figure better. So what you're doing is you're training a full model, say on MNIST or something. There you go. And then you wait some time. And then for large enough T, then you estimate the power law of the spectrum of the covariance, right?
Oh, so actually no. Before I even train, I'm using just the what's actually interesting. I'm calculating the infinite width in TK. So even though this is a real finite width guy, I calculate before training the infinite width in TK, and I diagonalize that matrix. I look at the eigenvalues and I look at the projection of the eigenvectors onto the labels.
I see.
And then from that, before I even start SGD, I already have a prediction for what these black curves, what their slopes should be.
I see.
And I'm only plotting them for the late times because that's where the power really gets in.
I see. I thought what you were doing was, because I thought that what was happening was something slightly different, but maybe you can tell me if you think this is possible at all. I thought that for different training times, you were actually gathering all your features and then computing the spectrum. And then my question is, if you were to do that for every single time, do you think that at some point the spectrum would, for example, begin rather flat and then over time converge to something that looks like a power law until it becomes stable, and then you would observe the decay that you actually fitted here? Do you think something like that would happen?
Well, that's a very interesting question. So this is almost more, I guess, in the feature learning regime, I guess, where you're saying that the features are changing, and then the eigenstructure of the kernel changes, but at
Exactly.
maybe that stabilizes, and then I still get a clean power law, but maybe a different kind of power law. So that is still kind of an active thing that we're thinking about. I don't have any concrete things to say much about that, but yeah, I think that's definitely an interesting question. And if you want it, we could chat maybe at the poster session or something if you're curious.
Certainly.
But I think that's a great question. So just generally, yeah. So the question is, if the kernel's changing because it's doing feature learning, but then after some point becomes stable, could I still predict basically these scalings, not with the initial kernel, but with a kernel maybe at some intermediate? Yeah.
Correct.
Great question. Yeah. I don't know. Yeah.
Okay, awesome. We'll follow up on the poster session. So maybe let's move on to the last contributed talk of this session. Zhihui, are you there?
Hi, Jerry. Yeah, I'm here. So how are you?
Terrific, great. Do you want to try sharing your screen?
Yeah, let me share the screen.
Hey Siri,
Is Siri going to give you a talk?
Yeah. Okay, so can you see my screen now?
Yes, perfect.
Try to move. Okay, you can see my move, right?
Yeah.
Okay, great.
Okay, awesome. So for this last contributed talk, it's really a pleasure for me to introduce Professor Zhihui, who received his PhD in electrical engineering from the Colorado School of Mines, where he was working with Michael Waking. He was then a postdoctoral fellow at the Mathematical Institute for Data Science here at Johns Hopkins, where I had the pleasure to meet him. He's currently an assistant professor in the Department of Electrical Engineering, Electrical and Computer Engineering at the University of Denver in Colorado. And he's done extensive work on non-convex optimization, signal processing, and machine learning. So Zhihui, the floor is yours.
Okay, so thank you, Jerry, for the nice introduction, and thank you for having me, and also thank you for organizing this wonderful, conference. Okay, so today I'm here to talk over recent work on understanding neural collapse, which has been introduced by Stephen Mellon. So so through some simple model. So this is joint work with Tianyu and Jerry from Hopkins, with with Jinxin from DU, and with Xiao and Qin from UMich, and with Tong from Google Research. So recently, we have seen many efforts and progresses on understanding deep learning. So based on various simplifications. So this includes like studying the deep linear networks, or study very shallow networks, or going to another extreme to study very wide networks. So this has been one successful. Example is called neural kernels, or NTKs, which has been mentioned in the Black's and in the Aarti's talk. Okay, so the good thing of NTK is that it ensures that gradient descent will find a global minimum of the training problems. But we know there is a gap between the practical training and the NTK training, which is called the lazy training. And also, so most of this work, focuses on the output of the network, which thus hardly provides much insight in terms of questions of what the network actually learns in terms of interpolating, extrapolating, or representing the data. So in that talk, we will focus on the classification problem. Deep learning classifiers usually consists of two parts. So for an input image, so the first part is a feature mapping, which we map an input image to a very long feature, so this will be the feature in the talk. Okay, and on top of the feature, we have a linear classifiers. Okay, so this is our network output, so which is simply as W times the feature plus Bayes term. Then we will learn the network parameters theta and the linear classifiers by minimizing cross-entry loss, which is the difference between the network output and the one-hot labels. And we will also add a weight decay. So throughout the talk, we will assume the data points are balanced in the sense that each class has the same number of samples. In case not, we can simply use techniques like data augmentation to make them balanced. Okay, so the recent work by Papi, Han, and Donald has revealed common outcomes of the learned features and classifiers across a variety of architectures and data sets. So that has been mentioned in the Stephen Mellon's talk. So, and we can expand it one by these right figures. So here, each small ball represents the features of each training samples, and the different colors represent different classes. the bigger ball with the same color represents the mean of the features, and the red ball represents the classifiers. Okay, so now let's formally introduce this phenomenon called neural collapse, which concerns the configurations of the learned features and classifiers. So the first property is called the within class variability collapse, which means the features of each class will collapse to the class mean with zero variabilities. Okay, and the second property concerns the configurations of the means of the features. So in particular, each class means has the same length and they are maximally distant. In other words, the angles between each pair of the means have slightly larger than 90 degrees. In particular, if we put each class means as a metric, then they will form a called a simplex equal angular time frame, or simply called as a simplex ETF. Third, there is a self-duality relationship between the means and the classifiers. In particular, the last layer classifiers are perfectly matched with the class means of the features in the sense that the lows of the classifiers will point exactly towards to the direction of the class means. Okay, so our work will have two contributions. So first, we will theoretically understanding this neural collapse through an unconstrained features model, which we will introduce soon. And this model, we will show that the training problem has a benign global landscape in the sense that local search algorithms like gradient descent will almost surely find the neural collapse features and classifiers. Second, we will explore the neural collapse properties to improve the efficiency of the training neural networks. In particular, we will show that training with small dimensional features and fixed classifiers will achieve similar or the same performance as large dimensional features and learned classifiers. Okay, so now let's talk this in details. As we mentioned before, a deep learning classifier consists of two parts. We first map the input to a feature, and then we have a linear classifier on top of like features. And then we try to train or to optimize this parameter theta in the feature mapping and the linear classifiers by minimizing this cross-entropy loss. However, this training problem is highly non-convex due to the nested layer structures in the feature mapping and also due to the nonlinearities. Since the neural collapse properties we mentioned before concerns the configurations of the features and the linear classifiers, so we will treat the features H as a free optimization variables. And then we will turn to study the optimization problems, which is only about the features H and the linear classifiers. Okay, so we call this one as an unconstrained features model because in this case, the features can move anywhere in the feature space, even though we do add a weighted decay on these features. So aside from aside for the purpose of simplifying the analysis, the rationality behind this unconstrained feature model is that modern networks are highly overparameterized, or the modern feature mapping are highly overparameterized in the sense that they can approximate any point in the feature space. Okay, so this is also called layer peeled model and has been recently used to study the neural collapse properties, which we will mention soon. And another thing is that you may notice that we do add the weighted decay on the features. Well, the rationality is that if we add a weighted decay on the feature mapping theta, then it is implicitly regularizing the features. Okay. So there are some, recent efforts on understanding neural collapse through this unconstrained features model or beyond. Okay. So most of this work on the cross-entropy loss will introduce some sort of regularizers on both the features and the classifiers. Okay. And under these settings, they have shown that any global solutions of this problem has neural collapse properties. However, because the problem is non-convex, it may have local minimum, and if we run gradient descent, it may converge to a local minimum. And also, the constraint formulations are not well aligned with practice, where we usually use the regularizers instead of the constraints. And also we have seen some works on understanding the neural collapse for the mean squared error loss. Okay, so in this work, we will study this cross-entropy training loss under this unconstrained feature model, and we have the weighted decay on both the features and the classifiers, and the classifiers includes both the weight matrix W and the bias term. Okay, so so our theorem says that as long as the feature dimension D is larger than the number of classes, then any global solutions of this cross-entropy loss have this neural collapse solutions. Okay, so here the features have zero global mean, and also we will see a collapsing phenomenon on the bias term in the sense that the bias term will become zero. We'll notice that if we constrain the features, say to be non-negative, which could be the output of the real unit, then the bias term will not be zero, but it will make up for the global mean of the features. Okay, so this concerns the global solutions of this cross-entropy training loss. Our second result concerns the global landscape of the training loss. In particular, so we show that these problems has benign landscape in the sense that it has no space local minimum, or in other words, every local minimum are the neural collapse solutions. And moreover, any other critical point that is not a local minimum has negative curvature direction in the sense that its hashing has negative eigenvalues, which can be escaped by many local search algorithms. So if you are familiar with the metric factorization problems, you may find, okay, these results are quite similar. And it's true, actually, it's closely related to the low-rank metric factorization problems. And the difference is that here we consider the cross-entropy loss, while in like low-rank metric factorization problems, we usually consider the least square loss. And also we have this, here we have additional bias term. And also the global landscape is usually derived under certain statistic properties for the low-rank metric factorization problem, like in metric sensing or metric completion problem. But here the problem is purely deterministic. Okay, so the takeaway message is that under this unconstrained feature models, the training problems has benign landscape in the sense that any local search algorithms like a gradient descent will almost surely find a local minimum. And we have shown that any local minimizers has this neural collapse solutions. So therefore, we will almost surely learn the neural collapse features and classifiers. Okay, so now let's use some experiments to verify our findings on practical network instead of this unconstrained feature models. Okay, so in particular, we will use a ResNet on CFR10, and the first one we will train the network with different training algorithms. So here we explore 3 learning algorithms, 2 first-order algorithms, the stochastic gradient descent and the ADAM, and 1 second-order method, the LBFGS. So here we plot the 3 neural collapse measures from left to right is within class variabilities of the training features, the between class separations of the class means of the training features, and the self-duality gaps between the learned features and classifiers. The smaller this quantity is, the more neural collapse. Okay, so from these figures, we can say that we can observe the neural collapse across different training algorithms, which is consistent with our benign global landscapes for the unconstrained feature models. Okay, so as we mentioned before, in our model, we do put the weighted decay on the features, but in practice, we will add the weighted decay on the parameters in the feature mapping. Okay, so there is a slightly gap here. Now we use experiments to verify that the gap is actually, very minor. So here we have shown the learning curves for this. So for the same 3 neural collapse measures, we can say that all of these 3 cases, all of these 2 cases have the same, or we can observe the neural collapse, phenomena. And if you may wonder, so like the testing performance, we are putting the number here, which we can say they are quite similar. Okay. So the message is that weighted decay on the parameters actually implicitly regularize the features. Now let's test the ways how neural collapse depends on the input data points. Okay, so here we use the same CFR10 data set, but we use a random labeling for them. And here we use a multi-layer perception so that we can easily verify the network widths. In these figures, we increase, so from top to down, we increase the network widths from 8 to more than 2,000. Okay, so in the first plot, we plot the neural collapse pressures of the within class variabilities. In the middle figure, we plot the self-duality gap. And in the third plot, or in the most right plot, we show the training error rate. Okay, so we also observe, what we observe is that as long as the network width is large enough, we will always observe neural collapse properties, and also we observe zero training error. We will also observe similar results for the random input images where each image has random pixels. Okay, so therefore, so this result is consistent with what people have observed for the zero training error. But it also tells us that the network actually memorizes the training data in a very special way, that it will map the entire input, so it will map the entire training class to a single point in the feature space. Okay, so now let's explore this neural collapse to help training to help training the networks. Okay, so first one is that we know we will always the linear classifiers will always converge to a simplex ETF. Then the first question is, why do we want to learn it actually? Why don't we just fix it as a simplex ETF? Well, so if we if we fix it as a simplex ETF, then actually we can save a lot of parameters. So ranging from 8% to more than 50% for different architectures. Okay, and the second one is that our results shows that as long as the feature dimension is larger than the number of classes, we will observe neural collapse. Therefore, we can just set the feature dimension D as the number of classes. So for example, set D equal to 10 for the CFR10. This can further reduce the number of parameters. For example, we can save more than 20% for the resonant 18. Okay, so here we compare the performance of the learned and the fixed classifiers. So on the CFR10, so here we use the resonant 15 because it will achieve the best performance. So here we compare 4 cities. This light blue corresponds to the standard setup, which is that we learned the classifiers and we set the feature dimension D more than 2,000. Okay, and this blue curve is that we keep the same dimensionality of the features, but we fix the classifiers as a simplex ETF without training it. This green curve is that we still learn the classifiers, but we fix the dimension equal to 10. And this red curve is that we fix the classifiers and also we reduce the dimension of the features to 10. Okay, and the left figure plots the neural collapse measures, which we can say we always observe neural collapse, but we can say that for the blue curve and the red curve, which corresponds to the fixed classifiers, it has more neural collapse. So that is because we fix it as a simplex ETF. On the middle and the right plot, we show the learning curves for the training accuracy and the testing accuracy. We will observe is that they all achieve on-par performance actually, or in other words, even training with the small dimensional features and the fixed classifiers actually achieve the same performance or will not reduce the performance. So this is also contrasted to the NTK theory, which will require the D to be large enough, but here we just fix D equal to 10. So there are many open questions. So for example, how can we study the middle layer classifiers? Okay, and also there are some questions, for example, like is neural collapse a blessing or curse? I'm not going to answer these questions because that really depends on like what the, under what the context actually. So here I'm trying to plot or drawing your attention is that I believe it will help us understand this generalization performance. Okay, so here we run the resonant 18 on only 3 classes, and we set the feature dimension to be 3, so that we can plot the features for each for each data point. on the top figures, we plot the features for the training data points. So the features, we plot the features for the training data points. So the first one is the initialization one, which you say are clustered, we kind of say, and the middle one is in the middle stage. And the most right figure is the features we obtained after training. Okay, sorry. So we do observe the neural collapse, and we also observe actually the same neural collapse at the testing data point, which we show at the bottom one, which says that because the network will not only collapse the training data point, it will also collapse the testing data point. This is why the neural collapse, the network can generalize well. All right, so the take-home message is that we show that under the unconstrained feature models, the network will always learn neural collapse features and classifies. And we also exploit these properties and shows that training with small dimensional features and fixed classifiers will not decrease the performance of networks. Okay, so thank you for your attention, and I will be happy to take any questions you may have.
Thank you so much, Zhihui. Are there any questions from the attendees or the panelists? I have a question, Zhihui. What do you think? What would you say it's the it's the biggest hurdle to move beyond this model where you only consider the last features and the classifier? Let's say that you now incorporate another layer. What is the main difficulty? Is it the extra non-convexity because now you have yet another factor that is multiplying your other ones, or is it that the map is non-linear because of the ReLUs?
Well, I think there are several reasons. One thing, as you mentioned, the problem is non-convex because we have ReLUs. The other reason is that I believe even with ReLUs, we can still show neural collapse for the first layer, or say if we have two layers. Okay, we can still show neural collapse, but we still don't have the inputs actually, because we know like if we have inputs, we will not observe neural collapse across every layers. We will have a progressively, progressively collapsing the inputs until the last layer, which we have neural collapse. So therefore, I think we need somehow to incorporate the inputs, which means then we can show like neural collapse in every layer. But I don't have like good answers yet. To how to incorporate actually the inputs actually to understand the neural collapse.
We'll have to continue thinking about it.
Thanks.
Okay, so if there are no more questions, this will conclude the second session of today. And now we have a short break. And after starting at 3, from 3 to 5, we have the first poster session where you can learn about these two works that were presented here, as well as many others. And then we will resume at 5 for the last session of today, where we are going to have some best poster updates, as well as the last feature talk by Rebecca Willett, which you won't like to miss. So see you everybody around in the poster session and later today in the last session.